Plate tectonics is a scientific theory that describes the large-scale motion of Earth's lithosphere. This theoretical model builds on the concept of continental drift, which was developed during the first few decades of the 20th century. The geoscientific community accepted plate tectonic theory after seafloor spreading was validated in the late 1950s and early 1960s. The lithosphere, which is the rigid outermost shell of a planet, is broken up into tectonic plates. The Earth's lithosphere is composed of 7 or 8 major plates and many minor plates. Where the plates meet, their relative motion determines the type of boundary: convergent, divergent, or transform. Earthquakes, volcanic activity, mountain building, and oceanic trench formation occur along these plate boundaries. The lateral relative movement of the plates typically ranges from 0 to 100 mm annually. Tectonic plates are composed of oceanic lithosphere and thicker continental lithosphere, each topped by its own kind of crust. Along convergent boundaries, subduction carries plates into the mantle. The material lost is roughly balanced by the formation of new crust along divergent margins by seafloor spreading. In this way, the total surface of the globe remains the same. This prediction of plate tectonics is also referred to as the conveyor belt principle. Earlier theories propose gradual shrinking or gradual expansion of the globe. Tectonic plates are able to move because the Earth's lithosphere has greater strength than the underlying asthenosphere. Lateral density variations in the mantle result in convection. Plate movement is thought to be driven by a combination of the motion of the seafloor away from the spreading ridge and drag, with downward suction at the subduction zones. Another explanation lies in the different forces generated by tidal forces of the Sun and Moon. The relative importance of each of these factors and their relationship to each other is unclear, and still the subject of much debate. Key principles. The outer layers of the Earth are divided into the lithosphere and asthenosphere. This is based on differences in mechanical properties and in the method for the transfer of heat. Mechanically, the lithosphere is cooler and more rigid, while the asthenosphere is hotter and flows more easily. In terms of heat transfer, the lithosphere loses heat by conduction, whereas the asthenosphere also transfers heat by convection and has a nearly adiabatic temperature gradient. This division should not be confused with the chemical subdivision of these same layers into the mantle and the crust. A given piece of mantle may be part of the lithosphere or the asthenosphere at different times depending on its temperature and pressure. The key principle of plate tectonics is that the lithosphere exists as separate and distinct tectonic plates, which ride on the fluid-like asthenosphere. Plate motions range up to a typical 10 to 40 mm year to about 160 mm year. The driving mechanism behind this movement is described below. Tectonic lithosphere plates consist of lithospheric mantle overlain by either or both of two types of crustal material: oceanic crust and continental crust. Average oceanic lithosphere is typically 100 km thick. Its thickness is a function of its age. As time passes, it conductively cools and subjacent cooling mantle is added to its base, because it is formed at mid-ocean ridges and spreads outwards. Its thickness is therefore a function of its distance from the mid-ocean ridge where it was formed. For a typical distance that oceanic lithosphere must travel before being subducted, the thickness varies from about 6 km thick at mid-ocean ridges to greater than 100 km at subduction zones. For shorter or longer distances, the subduction zone thickness becomes smaller or larger, respectively. Continental lithosphere is typically 200 km thick, though this varies considerably between basins, mountain ranges, and stable cratonic interiors of continents. The two types of crust also differ in thickness, with continental crust being considerably thicker than oceanic. The location where two plates meet is called a plate boundary. Plate boundaries are commonly associated with geological events such as earthquakes and the creation of topographic features such as mountains. volcanoes, mid-ocean ridges, and oceanic trenches. The majority of the world's active volcanoes occur along plate boundaries, with the Pacific Plate's Ring of Fire being the most active and widely known today. These boundaries are discussed in further detail below. Some volcanoes occur in the interiors of plates, and these have been variously attributed to internal plate deformation and to mantle plumes. As explained above, tectonic plates may include continental crust or oceanic crust, and most plates contain both. For example, the African plate includes the continent and parts of the floor of the Atlantic and Indian Oceans. The distinction between oceanic crust and continental crust is based on their modes of formation. Oceanic crust is formed at seafloor spreading centers, and continental crust is formed through arc volcanism and accretion of terranes through tectonic processes, though some of these terranes may contain ophiolite sequences, which are pieces of oceanic crust considered to be part of the continent when they exit the standard cycle of formation in spreading centers and subduction beneath continents. Oceanic crust is also denser than continental crust owing to their different compositions. Oceanic crust is denser because it has less silicon and more heavier elements than continental crust. As a result of this density stratification, oceanic crust generally lies below sea level, while continental crust buoyantly projects above sea level. Types of plate boundaries. 3 types of plate boundaries exist, with a fourth mixed type, characterized by the way the plates move relative to each other. They are associated with different types of surface phenomena. The different types of plate boundaries are: transform boundaries occur where 2 lithospheric plates slide, or perhaps more accurately, grind past each other along transform faults, where plates are neither created nor destroyed. The relative motion of the 2 plates is either sinistral or dextral. Transform faults occur across a spreading center. Strong earthquakes can occur along a fault. The San Andreas Fault in California is an example of a transform boundary exhibiting dextral motion. Divergent boundaries occur where 2 plates slide apart from each other. At zones of ocean-to-ocean rifting, divergent boundaries form by seafloor spreading, allowing for the formation of new ocean basin. As the continent splits, the ridge forms at the spreading center, the ocean basin expands, and finally, the plate area increases, causing many small volcanoes or shallow earthquakes. At zones of continent-to-continent rifting, divergent boundaries may cause new ocean basin to form as the continent spreads. The central rift collapses, and ocean fills the basin. Active zones of mid-ocean ridges and continent-to-continent rifting are examples of divergent boundaries. Convergent boundaries occur where 2 plates slide toward each other to form either a subduction zone or a continental collision. At zones of ocean-to-continent subduction, the dense oceanic lithosphere plunges beneath the less dense continent. Earthquakes then trace the path of the downward moving plate as it descends into asthenosphere. A trench forms, and as the subducated plate partially melts, magma rises to form continental volcanoes. At zones of ocean-to-ocean subduction, older, cooler, denser crust slips beneath less dense crust. This causes earthquakes and a deep trench to form in an arc shape. The upper mantle of the subducated plate then heats and magma rises to form curving chains of volcanic islands. Deep marine trenches are typically associated with subduction zones, and the basins that develop along the active boundary are often called foreland basins. The subducating slab contains many hydrous minerals which release their water on heating. This water then causes the mantle to melt, producing volcanism. Closure of ocean basins can occur at continent-to-continent boundaries. Collision between masses of granitic continental lithosphere. Neither mass is subducated. Plate edges are compressed, folded, uplifted. Plate boundary zones occur where the effects of the interactions are unclear, and the boundaries, usually occurring along a broad belt, are not well defined and may show various types of movements in different episodes.